So we're going to start with computer arithmetic and sources of error, because it helps if we understand what our computer is actually doing. And then once we understand what the computer is actually doing, we're able to identify errors that we may have in our solutions and things that we can do to fix that. Okay, so first section is computer representation of numbers. Okay, so here we want to talk about the floating point form that is used to represent real numbers. So we use a floating point form. And it depends on your actual computer. So let's say we have a number X. So it is represented by the sign of X, that's the plus or minus, and then a decimal A1, A2, all the way up to AN. And then this is with respect to some number beta, and then it's multiplied by beta to the E. Now I know that looks weird. It should look weird, okay? So beta is the base of the system. And so beta is either equal to 2, 8, 10, or 16. The AI, these are all digits in the base beta system. So for example, if it is base 2, then the only numbers that will exist will be zeros and ones. If it's base 8, the only numbers that will exist will be 0 through 7. Okay, so you can have A0 is less than or equal to AI is less than or equal to beta minus 1, and A1 is not equal to 0. So that's A1. E, well, this is an exponent. Or a characteristic. And we have some number M, which is less than or equal to E, which is less than or equal to capital M. And then M, little m and capital M are integers. And these vary by computer. Usually little m is minus capital M, or sometimes little m will be minus capital M plus or minus 1. Okay. And then lastly, our dot A1, A2, all the way up to AN. This is called the mantissa. all right? And it contains n digits. Okay. So now, based on what your computer is, any number which contains more than n digits has to be shortened to that length in some way. And so that's what changes our precision of any calculation. Okay, so numbers containing more than n digits must be shortened. So if your computer only holds 16 digits and you're trying to utilize a number that has 32 digits or it continues, then anything after the first 16 will be chopped off, just gone. Okay, so single precision floating number. So we have single precision. And we also have double precision. And the difference is the length of the mantissa. Okay. So for some computers, single precision may be 8 digits, whereas double precision may be 16. Okay, so here's an example. So let's say you have beta is equal to 8. So therefore, your computer is holding everything in it in terms of base 8. Now we're thinking that it's adding the numbers in base 10, but it may not be. It will be adding in base 8. So let's see how we do this. Okay, so we want to write the number 426 in base 8. Then we're going to have 1, 8, 64, and 8 cubed is 512. So how many 64s go into 426? So that's 6. And then 6 times 400, 6 times 64 is equal to 384. And that means, and I subtract that from 426. So that leaves me 42. So how many times does 8 go into 42? Well, that's 5. So that's 40. So this number right here, oh, I got rid of it. What was it? 4 times, no, 6 times 6, 6 times 64. That was 384. So this is 384. And then this is 40. So if I add 40, that gives me 424. And then I'm going to need 4 ones. And that will give me 4. Okay, so in base 8, the number 426 is actually 654 base 8. Okay, so 426 which we normally use is base 10, turns out to be 654 base 8. Now this can even be more difficult when you have a number like 2,405. And now I have 0.17. Okay, so now this becomes even more difficult because how is the computer storing this in base 8? Okay, so this the first one didn't have a decimal. This one has a decimal. So this one so again, we had 1, then we had 8 to the first, we had 8 squared, we had 8 cubed, that was our 512. Did I do that right? I feel like that's not right. 8 times 64 is 512. Oh, that is correct. Okay. All right. And so then this becomes 8 now. So this is 8 to the 0. This becomes 8 to the -1. And this becomes 8 to the -2 because we're going to have a decimal. Okay. So 2,405. That's actually going to require 2 512s. So 2 512s is equal to, so this piece gives you the 1,024. And then I'm going to need 4 of the 64s. Oh, actually, I'm doing it backwards. I apologize. I'm actually trying to, I apologize. I'm doing this number base 8. I'm trying to see what it actually equals in base 10. I'm reading my notes backwards. So this thing is 2,405.17, and that is base 8. Okay, so what is that in base 10? Well, base 10, so this is going to equal 2 times 8 cubed plus 4 times 8 squared plus 0 times 8 to the first plus 5 times 8 to the 0 power plus 1 times 8 to the -1 plus 7 times 8 to the -2. And when you add all that up, you end up with 1,285.2344. And that's what we would see as base 10. Okay. So the computer holds things differently than how we think. All right, let's look at sources of error. So that was A, B. Okay, so we have two types of error. There's actually what we call true error and relative error. Does anybody know the difference? Okay, well, let's first define true error. So true error is the value of a number and I'm going to call that X true minus its approximate value. And its approximate value, I'm going to call XA. So true error, we're going to call that capital E sub T. All right. This is the error in X. And it's basically equal to X true minus X approximate. Many times you will see it in absolute value. Okay, so the approximate error, the relative error, which is much more useful, is the percentage of error in the approximate value relative to the true error, relative to the true error, to the true value. So I'm going to call that epsilon, epsilon T. And this is to take the true error, subtract the approximate error, and then divide it by the true error. Okay, so let's look at an example. So if I measure something, so here's, I'm going to measure a height, and I get 49.1 inches. Okay, and the actual value, so that's the approximate. The true value is 50 inches. So therefore, the error is to take 50 minus 49.1, and I get 0.9. Okay. So now 0.9 is not that bad. So we're going to take 0.9 now and divide by. So now I'm going to take 0.9 and divide by 50. Oh, I should say, and we multiply this by 100 in general. And multiply this by 100. And I get 1.8. So I get 0.018 times 100. And so I can see that that's basically a little over almost 2%. But now if I was to measure a height, and I got 1.1 inches, and its true value is 2 inches, then my true error is equal to 2 minus 1.1. So that's still 0.9. So it looks like they basically have the same kind of error. But if I look at the relative error, if I take 0.9, divide by 2, and multiply by 100, that's 45%. So relative error gives you an idea of how poor your solution is relative to the answer you're supposed to get. Okay, so here I was supposed to get 50, I got 49.1. My approximation is not too bad. Whereas I had 1.1 and I actually was supposed to get 2, my approximation is pretty bad, 45% off. Okay, so that's how we look at error. All right, let's define round off error. Oh, so I want error propagation and numerical stability next. So round off error, this arises because the arithmetic performed on the computer involves numbers with only a finite number of digits. So suppose we have this. You have some x it's the sine of x times a1, a2, an plus 1, and this number actually keeps going, maybe like pi, 10 to the e. So here beta's 10. All right. Then this is how it's going to compute the round. So it's going to do a floating point of x. We're going to do one of two things. It's going to take the sine of x times a1, a2, all the way up to an times 10 to the e. And that's if an plus 1 is less than 5. So we're going to round down. So we've seen this before, okay? We had to do this back in junior high, actually. Round the number up or down to the nearest tenth or hundredth or thousandth. That's exactly what these are. This is the 10th digit. So here's the 10th digit, the 100th digit, the 1000th digit, etc. Okay, so it will round down if the next number is between 0 and 5, or it's going to take the sine of x. It's going to take this number and then it's going to add to it 0, 0, all the way up to a 1. And this is 10 to the minus n, a 1 in the nth place. And this is 5 is less than or equal to an plus 1 is up to 10. So this is rounding up. Okay. Any questions about that? This is an abstract way of thinking about rounding. We're used to seeing it very concrete. Okay. So what's the error in the floating point approximation of x? Okay, well, that's just x minus FL of x. All right. Well, that's going to take, and you're going to get two different things. Here in the first one, you're going to get 0.00 all the way up to an plus 1, an plus 2, and it just keeps going times 10 to the e. And this is when 0 is less than or equal to an plus 1 is less than 5. But you're going to get just an plus 1, an plus 2, times 10 to the e minus n, because that we're taking into account that last piece, 5 less than or equal to an plus 1. less than 10. So in general, so when we take and look at the absolute value of that error, and that is equal to the absolute value of x minus FL of x. This is less than or equal to 1/2 10 to the e minus n, okay? And so there's actually a proof in the book for general B. General beta, I don't believe I said general B. Okay, so now what's the relative error? Well, the relative error, we're gonna look at the absolute value of the relative error. That's just to take the true error and divide that by what we're supposed to get, which is x. So therefore, I'm going to get which one am I using? I'm going to do the second one. So we're going to get point an plus 1, an plus 2, 10 to the e minus n, and we're going to divide that by point a1, a2, all the way up to an plus 1. Remember, this kept going, times 10 to the e. So now this is less than or equal to 1/2 10 to the minus n divided by point a1, a2, an plus 1, and so therefore this is then equal to 1/2 10 to the minus n divided by 0.1. Which is the smallest value it could possibly be. So I'm trying to maximize the area. So the smallest this can be, the smallest this A1, A2, this is the smallest possible value. So then that becomes equal to 1/2 10 to the minus n plus 1. Okay. So in general, we get that the absolute value of the error in FL is equal to the absolute value of x minus FL of x, and that's less than or equal to 1/2 beta to the e minus n, and then the absolute value of the relative error is less than or equal to 1/2 beta to the minus n plus 1. Okay, so let's look at an example, because right now it seems very abstract. Okay, so let's approximate pi to the 4th to 3 with only 3 digits. Okay, so now if I use the full 8 digits, so I'm going to have pi to the 4th is going to be 3.14159 2654 14159 2654 to the 4th power. Okay, I could use more digits, but that's what I have available. So this comes out to be 0.974099108 times 10 squared. Okay, so as you can see, this is the point A1, A2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to A10, and then times our 10 to the E. So E is 2. Okay. Now I'm going to do a round for this. So FL of pi to the 4th. I can only have 3 digits. So that's going to give me 0.974. It's going to look to the next number and it's going to see a 0. So it's going to round down times 10 squared. Okay. Kayla, you look skeptical. You okay? All right.
Yes.
Okay. So if I just put this big long number into my calculator or into the computer, this is the number I would get. But if I'm going to, so actually if I'm holding 10 digits, you can see that for a 10-digit computer that I would be holding that many numbers. So I would have that. All right. And so it would be 10 squared. Remember, beta would be 10 here. All right. And so now I'm only going to be allowed, if by chance, I'm only allowed to use 3 digits. This is what I have. So let's check the error. Okay. So from our formula, it says that the absolute value of the error in what we're calculating for pi over 4 should be less than or equal to 1/2 10 to the E minus N. Okay, so N is 3 because I'm trying to approximate it to 3 digits. So N is 3, and this is 10 squared. So therefore E is 2. So this should be 1/2 10 to the 2 minus 3. 1/2 times 10 to the minus 1. So this is 0.05. So the true error should be less than 0.05. That's the true error. Okay. And the relative error well, that should be less than or equal to 1/2 10 to the minus n plus 1. So that is 1/2 10 minus n, so that's minus 3 plus 1. So that becomes 1/2 10 to the minus 2, which is 0.005. Okay, so this is predicted. By our formula. Okay, so let's see what we actually get. So what we actually get is if we take the absolute value of pi to the 4th and we subtract off the floating point error answer. So the floating point answer, so we actually get then the absolute value of 0.9740909 and then I'm going to subtract off the point, what was it, 974. This comes out to be 0.009099108. And then this becomes 0.0000933. Okay, so that's round off error. So let me see how my notes went. Okay, definition. All right, so let's define chopped error now. Okay, so chopped error is a little bit different. Okay, there is no looking at the next number. We just chop it off. So in some cases, the chopped error may be the same as the round off error, and in other cases, it may not. Okay. So the chopped error is just for us FL of X is going to be the sine of X times dot A1 we just stop. We don't even care about what's afterwards. We just quit. Okay. One other type of error we also have is, so let's look at that in terms of mathematical truncation error. So mathematical truncation error. So this is a process. So this is the method of approximating an infinite process by a finite one. And we're all familiar with this, okay? So one example is the Taylor series. So I have f of x is the square root of 1 plus x. All right, so how do we develop the Taylor series to this? All right, so we want to find the Taylor series approximation about x equals 0. Does anybody know what the special name is when you have a Taylor series about x equals 0? Has a special name.
It's called Maclaurin series.
That is correct. It's called the Maclaurin series. Okay. This is going to be okay. So first thing is when n is 0, the 0th derivative is literally just 1 plus x to the 1/2 power. And so when I evaluate that at x equal to 0, then I just get 1. When I do the first derivative, I get 1/2 1 plus x to the minus 1/2 power. And when I evaluate that at x equal to 0, I just get 1/2. So the next one is the second derivative. And so now I'm going to get 1/4 times 1 plus x to the negative 3/2. And then when I evaluate that, I get 1/2. And I feel like there's a negative missing. And this is not -1. That's not 1/2. That should be negative 1/4. Okay. And if I go 3, I'm going to end up with 3/8 times 1 plus x to the negative 5/2. And when I put in 0, I get 3/8. I'll do one more. Fourth derivative, I'm going to get negative 15/16 times 1 plus x to the negative 7/2. And when I evaluate it at 0, I get negative 15/16. Now this always works really nice when there's a formula. So if you can figure out the formula, it's beautiful. But sometimes we can't figure out the formula. So we can write our Taylor series, f of x equal to the square root of 1 plus x. So the first is 1 plus, we end up with 1/2 x to the first power minus 1/4 times x squared plus 3/8 x cubed minus 15/16 . Okay, we have 10 minutes left. 15/16 x to the 4th plus ... So this is an infinite approximation. To the function of square root of 1 plus x. Okay. And of course, this is for x very small. In fact, for us, the absolute value of x, I believe, has to be less than 1, but it's for x very, very small. Let me say x much, much less than 1. Okay. And the square root of 1 plus x is almost 1 plus 1/2 of x when x is really, really small. Okay. All right. So this piece right here all right, is what we call a mathematical truncation for this function. All right. And in fact, this is actually the Taylor polynomial. Of degree n equals 1. All right, so let's suppose here's our question. All right. Suppose we're looking for an error, or the absolute value of our error, to be less than 10 to the minus 2, or 0.01. All right, so how small does x need to be all right, to use only the two terms as an approximation. Now, if you go back to calculus, there's actually a theory that tells you exactly what your error in your approximation is for a Taylor polynomial. So there are a couple of ways we can figure this out. So here's the first answer. All right, let's substitute x equaling 0.4. All right, well, the square root of 1 plus 0.4 is the square root of 1.4. And that is 1.1832 and some other digits. Okay, and 1 plus 1.4, 1 plus 1/2 of 0.4 is 1.2. So now if I look at the error, it's the absolute value of 1.1832 minus 1.2 and that is 0.016. Oh, that's not good enough. That's 7, 8, that's some other stuff going on. So obviously that didn't work. Okay, so let's substitute x equal to 0.3, because now I'm going to go smaller, because the first one didn't work. So now I get the square root of 1 plus 0.3, and I'm going to take the square root of that. And now I get 1.140175, some other numbers. And then when I do 1 plus 1/2 of 0.3, I get 1.15. So now when I do the error, I get the absolute value of 1.140175 minus 1.15. And I end up with 0.0098. And that is indeed less than 0.01. But you know, this whole method was trial and error. And it doesn't tell me about, so I know I have to be less than I know 0.3 works, but does 0.31 work or 0.32 work or 0.33 work, or I don't know. So it's not the best method. So there's another way we can try it. Let's look at A2. Let me see how much time I have here. Oh, I got 3 minutes. Okay. So here's my second answer. All right, so let's just look to leading order. So I go back to what I had before. And this was my approximation. Okay, so this was my approximation. So I have the square root of that is equal to that. So let's subtract off the first piece. So let's say the square root of x then, square root of 1 plus x. And we're going to subtract off the 1 plus a half x. Okay, when we subtract that off, it leaves minus 1/4 x squared plus 3/8 x cubed minus 15/16 x to the 4th plus dot, dot, dot. Now we know that we know that x is less than 1. So therefore, this is the largest term. So we're going to, uh-oh. Oh, I know. Oh goodness, let me fix this error before we go. Oh my gosh, I forgot I have an error in my notes. Woo, woo, woo. Let's go back. This is over 2 factorial, and this is over 3 factorial. And this is over 4 factorial. Oh my goodness, I forgot. It's a Taylor series. Forgot my factorials here. So this is over 2 factorial, and this is over 3 factorial. So therefore, this first term here is actually minus 1/8 x to the x squared. Plus dot, dot, dot. Okay, we're going to pick up here we'll pick up here on Thursday.